So, ladies and gentlemen, let me start the morning session of the last day of this wonderful conference. And during this time, we will have two plenary lectures, and I'm sure that both lectures will be wonderful. So it was worth to stay until the end of this conference. The first speaker is Tommaso Flaminio. He's a tenured scientist. I like Italian title, Scientifico Titular. It looks wonderful. At Artificial Research Institute of Spanish National Research Council in Barcelona. So he works with a famous group of people led by Francis Esteva. He graduated mathematics in the University of Siena in 2003 and obtained his PhD in mathematical logic and theoretical computer science in 2006. Well, his topics are especially knowledge representation, reasoning in logic, fuzzy algebraic and model reasoning under uncertainty, and also on logic for conditionals and counterfactuals and belief change. His age index is 18, and he has over 1,300 citations. What is interesting, you can find several kinds of information about the number of his papers, because in Google Scholar you will find the number 65. On some other list you will find the number something like 120. And here I have written 80 papers. So it's a certain sort of medium. Well, his talk, as you can see, probability theory and fuzzy logical cooperative. It's very interesting because, say, probability theory, which is a mathematical model of uncertainty, and Leibniz, whose mathematical model is fuzzy logic, are two sides of a more general phenomenon, which I may call indeterminacy. But for sure, there are different things and require different models. Probability theory is mostly on measure theory, while fuzzy logic is about various kinds of algebra. So I'm quite curious what will be surprising on your talk, and so I give you floor.
Thank you, Willem, for the really nice introduction. Let me see how it works. Yeah, oops. Okay, so yes, well, I will explain the title in a couple of minutes. Let me first of all start with a disclaimer, which is the following. Oops, just this one. So whatever weird claim you will hear this morning are mine, right? So the topic I will talk about is based on research that we have been done with Sara Ugolini from the institute where I also belong, and part of it also with Sandro Preto from the ABC University in Brazil. So it is based on theorems that we prove together, and those should not be discussed. But the claims that I try to convince you about that builds on these results are just mine. So whatever would be weird, strange, wrong claims is my responsibility, okay, not their responsibility. So the paper, the discussion I will present is based on a series of papers, actually a couple of papers that have been co-authored by Sara and Sandro. But let me say also that the claim I would like to present today comes from long discussion. I've been inspired by a lot of people. So sometimes you just look at the co-authors, but the final conclusion you arrive after some research actually comes from many other contributors. No, so I put the list here, which is of course not exhaustive, but I would like to keep it there just in case you want to see and recognize some names. It's also, so let me now, and those are the two papers on which from where the results I will present you are about. The first one, they're quite recent. The first one is co-authored with Sara, And it is a paper that appeared last year, 2 years ago. And the other one is in collaboration also with Sandro. It is about, well, the message behind both papers is similar, and it is exactly the thing I would like to explain you today. Okay. And so let me explain the title, because for those of you who know the famous Lofty-Zadeh paper, probability theory and fuzzy logic are complementary rather than competitive, that this paper aims at, to clarify the situation at a certain point, no? Because it was published in 1995. It was kind of confusion between what is fuzzy logic, what is probability at that time, let's say, mainly from the, also in the applicative perspective, from the point of view applications. And still today, I think there are some papers that do not clearly identify which is the role of one theory and the role of the other. So keeping them complementary in the application means that you should know where to apply one theory and when to apply the other one, right? So which are the example to which fuzzy logic applies, which are the example to which probability theory applies. And I will explain this in a very short while. Curiously, in the same year, 1995, this other paper appeared, quoted by Peter Hayek, Luis Godo, and Francesco Esteva, whose title is also quite inspiring, which is probability and fuzzy logic. So it's rather than being complementary or competitive, this probability and fuzzy logic. And what they did in that paper is to introduce the logic that I will also present you in a couple of slides, and which is the basic step of the construction that I will show you along this talk. The logic is a probability logic built over a fuzzy logic. So the two things, they start already cooperating in this sense in the definition of the logic that Peter, Luis, and Francesc studied in the same year where Zadeh published that paper. So, and also another thing that I would like to say is that when I claim that the two theories are cooperative, they are cooperative also because they are complementary, because otherwise they wouldn't be able to cooperate. So they cooperate because they are two different theories, and you have to understand when and why they are not the same. Okay. So in particular, if we have to keep them separated and we have to understand where to apply one or another in application, is that when you formalize the logical mathematical models of the two, there are so many similarities that allows to somehow to identify them at a certain point. Okay, this is the thing I will try to convince you. No, I mean to present today. Okay. So what are the ground ideas? Let me just very briefly recall what are for me probability theory and fuzzy logic. Right? For probability theory, I understand much more the logical setting in which probability is embedded. So the probabilistic reasoning, if you want, not probabilistic quantification, right? So for me, probability theory is a kind of branch of logic, but also philosophy, mathematics, computer science. They study the quantification of uncertainty of unknown events, so something that is not known right now, but it will appear. It will be eventually decided if true or false, or partially true or partially false in the future. And also their combination. So if the probability of some event is this value, what will be the probability of another event? This is a kind of reasoning that you do in probabilistic settings. So when you reason under uncertainty. Fuzzy logic, again, is a branch of logic, philosophy, mathematics, computer science. This is the quantification of vagueness. This is also what Willem was supporting before. So uncertainty is a philosophical phenomenon, and vagueness is another one. Right? So, I mean, that's why they should not be confused. This is why they are complementary, and they should be kept complementary. Just to clarify once and for all, the distinction, if I have a glass which contains water, but 1 of 10 is poison, we can say that 1 over 10 is the true degree of the liquid inside is poisonous. Right? While if I have 10 glasses, 9 of which contains water, and 1 is full of poison, the probability of getting 1 which is poison is 1 over 10. So the same number represents here the vagueness of a statement, here the uncertainty of another statement. Right? This is the basic distinction. So, given this very rough introduction, let me go to the kind of formalization of the ideas. So we already saw that there are differences between vagueness and uncertainty, probability and fuzziness, if you want. But when you go to the mathematical formalization of the two theories, you meet many common points. One of them, for instance, is that vagueness and uncertainty are quantified using real numbers, and usually the real scales between 0 and 1. This is a convention, but I mean, we use the same convention in both cases. This is also another nice common property that classical logic more or less is seen from both theories, right? Why? Because classical logic is, 0-1 logic. Okay? So classical logic is a particular case of both theories because it is a logic of certain proposition, but also a logic of precise proposition. Okay, so if I want to state something which is true, totally true, you would use classical logic, but also if I want to state something that is certain now, I will say, so today is Friday, doesn't need to be quantified uncertainty. This is not uncertain, this is true, right? Today is Saturday is false, that's it. So in this sense, they have this common ground, so to say, the two theories, probability and fuzziness. On the other hand, again, in the logical formalization, we start meeting the different behaviors of the theories. The first one that maybe is the best well known is truth functionality. So what it means is that probability logic, for instance, is not truth functional, while fuzzy logic, at least in Hayek approach, I will follow Hayek approach to fuzzy logic, is truth functional. What does it mean? It means that, for instance, if you want to compute the probability of a conjunction of formulas, and you know the probability of both components, you cannot compute the probability of the conjunction because you have to know if the events, for instance, intersect, if they are disjoint. So probability logic is not truth functional. Fuzzy logic in Hayek approach is truth functional. So you evaluate the variables, and then you just use the function t-norms, t-conorms implication to compute the truth values of compound formulas. The other one, which is slightly less known, but is a really powerful tool in the study of logic in general, is algebraizability. Algebraizability in rough sense means that you can use algebraic methods to study the syntactic theory you are interested in. Fuzzy logic is algebraizable, again, in Hayek approach, and this is one of the main results contained in Carlos Noguera's thesis, if you want. Probability logic is not. Probability logic doesn't have an algebraic semantic, and this is what also Willem was claiming at the beginning, not this morning. So probability logic is not about algebra, in a sense. Doesn't have an algebraic semantics in the sense of algebraizability or algebraizable logic. And this is totally true. But it's a pity. It's a pity because algebraizability gives very strong and beautiful tools to study the syntactic property of a logic. So for instance, this is collected in a series of results that are called bridge theorems that says, for instance, if you want to study the interpolation on the syntactic side of a logic, you can totally equivalently study the algebraic variant of interpolation, which is called amalgamation. If your logic is algebraizable, and you don't want to study the syntax of the logic, you can study the algebras. If the class of algebras, the semantics for your logic, it does have the amalgamation theorem, then your logic has the deductive interpolation result. Okay. Other examples are unification, generalization, and others. Okay, I will touch these points maybe at the end of the talk. So the message here is that it would be nice if you could use the tools of algebraic logic in the study of, for instance, probability theory, or in general in the study of uncertainty. Because uncertainty is not algebraizable, but it would be nice if we could use at least some tools from there. Okay, this is the more or less ground on which we will move. Now, let me be precise on what is the logic that we will actually consider this is the basic logic, because then this logic can be extended in so many ways to encode and to study different measure of uncertainty, to add expressive power, a lot of things. But the basic logic is the following. So the idea is to start with a very specific fuzzy logic. Now, I will not speak about fuzzy logic in general, in the sense of theory of fuzzy set, but I will concentrate on a specific fuzzy logic in the sense of formal fuzzy logic. And our setting would be Lukasiewicz one. So Lukasiewicz logic is our ground language, and it's our ground logic. And the reason why Lukasiewicz, they choose Lukasiewicz, will be evident, I hope, in a short while. So we have, as usual, a language countable set of variables, connective plus negation and 0 of type 2, 1, 0. Formulas can be, I mean, other connectives can be defined more or less as usual. The implication of this logic is the material one, as in classical logic, so it's defined by the disjunction. Then you have the lattice operation, the top, which is the negation of, so true is the negation of false, and many other connectives, and the language is actually quite rich in this case. Lukasiewicz logic is algebraizable in the sense of Plot-Pigozzi, so we have an equivalent algebraic semantics. So what it means is that whenever you want to check, for instance, if an equation is true in your logic, you just have to check it here, because the logic is algebraizable, and the semantics, so the algebraic semantics is up to equivalences. Is the algebra defined on the real unit interval with these two operations, where this is the truncated sum, negation is standard negation, and 0 is the bottom element of 0, the real number 0. Okay. Now I think it is already evident why we need this logic to encode probability, because here we have a connective that behaves more or less as a sum, and probability is an additive measure. So additivity needs to be axiomatized, that operation. So you need the sum in the real numbers to say my measure is additive. What it means that if you want to study different measures which are not additive, you can use another logic. But for probability, Lukasiewicz logic is the best thing. So again, Lukasiewicz logic is not a probability logic. So it alone cannot deal with probability, for instance, because Lukasiewicz logic is truth functional, probability is not. So I mean, we have to break somehow truth functionality if you want to deal with probability reasoning in this setting. And the way to do it is to extend the language with a unary connective or a modality, if you want, that interprets formulas like p phi as phi is probable. And then the idea is that the truth value, in the fuzzy logic sense, the truth value of that formula represents the probability of phi. Okay? Now we already start mixing things, because the truth value represents the probability. So the fuzziness becomes an uncertainty value. This is the mathematical formalization. There is nothing philosophically deep at this level, just mathematical formalization. So the way to do it is to build a language, which is what is called a two-layer language. At the first layer, we have events, so the subject of probability. Then we will add to these events the modality P, and then we will combine with Lukasiewicz connectors. So at that level, we are truth functional. The truth functionality is broken in passing from events to probability values. So let me show you the picture. We have events here, with classical events. In this case, we are dealing with classical probability. So classical events that are representable in Lukasiewicz logic, of course. Once we have this formula here, we can add P to this formula. So for instance, you have a variable xi, pxi is a formula. If we have negation of phi, p of negation of phi is a formula. And then you close that are called atomic model formulas, you close them under the Lukasiewicz connective. So you can have sum of basic probability formula, implication of best probability formulas, and so forth. And this is it. The language doesn't allow any other specification. So for instance, you cannot use this operator P in a nested way. So you cannot write P of phi. Once you do P of phi, you're done. P is not, you cannot use it anymore. Also, you cannot mix this part, you cannot write phi implies P of psi, right? So this is not allowed. So what it means is that eventually the formulas that we have are just Lucas-Sage formulas, where instead of variables, you have atomic probability formulas. And that's it, because the basic thing are formulas of this kind. These are Lukasiewicz formulas, some, and those two are regarded just as new variables in the language. This will be a way to see this language. So the language is not as rich as we would like, but still is enough for axiomatizing probability measures. Because with this language, although it's quite poor, we can write a bunch of axioms that actually corresponds to the axioms, the common axiom of probability theory. The first one says that the probability is normalized, so the probability of 0, if you want, or the probability of top is 1. The second one, which is also well-known axiom of the modal logic, is the K axiom that essentially allows to show monotonicity of the operator P. And this is additivity, which is not written with the plus, it is written with the implication, but the implication is material in Lukasiewicz. So, I mean, this is exactly what it says. This says when, if you can make the exercise and show that when phi and psi is 0, then this is the sum of P phi and P phi. This is Lukasiewicz sum. Okay. So again, the language is not so expressive, but still can write axioms enough. So it's sufficiently strong to characterize probability measures, at least at the syntactical level. Semantics is made in terms of probability measures. So of course, you want to have a probability logic, so you will need to interpret your formulas by a probability measure. I'm skipping some details here on how to interpret formulas. Essentially, the idea is that when you have a compound Lukasiewicz formula on these variables, right, on the variables P phi 1, P phi k, like this, then what you do is to use mu, which is the model you have, the probability function mu. You apply it to the events that are the basic events of your formula, and then you compound the outside value, interpreting those are real numbers. And this is the trick of using the double interpretation. Those are real numbers, so you interpret this term here in the algebra, in the MV algebra on the reals, and you compute the value by the truth functionality of the connectives. Again, truth functionality is broken at this level, but it works at this level. At the outer level, it works. It is truth functional, this Lukasiewicz. And what is the main result of the paper that Peter, Francesca, and Luis proved is that published in 1995, is that in fact the logic is sound and complete with respect to these models. So it's a proper probability logic, if you want, right? So it's a fuzzy logic built on Lukasiewicz. It is complete with respect to probability models. So again, yes, probability theory and fuzzy logic are distinct, but, right? There's already a but that I would add to this at this point. Let me give you a hint on how they prove the theorem, because this is the basic thing that allow me then to explain my subsequent claims. The point is that the two languages are interdefinable. Not in a very efficient way, but in a way that it works for completeness, at least. So again, what I said before is that if you have a formula in this probability logic, if you regard the blue atomic formulas as variables, and you add them to the language as new variables, then you have just the Lukasiewicz formula, because now the P disappeared. And vice versa, you can take a formula of Lukasiewicz and add P on top of these variables, and you get the probability formula. Those are used in two different ways, this translation. The first one actually is used for the completeness of the logic. The other one is used for other reasons, not even in that paper, but in other papers have been used also this other translation. But this is interesting to see how actually two languages can be somehow defined one into the other. So regarding the first translation, you start with formula or your deduction, if you want, in logic FP, so formula phi that uses psi. What you do is to translate these two formulas in Lukasiewicz language with these new variables. Then you have to translate the axioms of probability that are formulas of that kind. You can translate the axiom. This becomes a theory in Lukasiewicz logic. And also this translation, which is, I mean, it's not just a syntactic translation. This is a translation that preserves validity. This is interesting. So if from phi deduce psi, then the translation of phi deduces the translation of psi together with the axioms that translate probability axioms. So the theory that translates probability axioms. And then, since Lukasiewicz is complete with respect to the reals, to the algebra on 0, 1, you use Lukasiewicz completeness, you go to the real numbers, and then what happens? That every model of this part is a model of this. But if an evaluation is a model of these two parts, it is a model of this in particular, right? But a model of this axiom is a probability, because it is an evaluation into the reals that satisfies all the axiom of the translation of the axiom of probability measures. So it is a probability function. And this is show the completeness. Very easy. We'll go back to this translation in a while. The second translation, the one that goes from Lukasiewicz to FP, is less studied. It's interesting because we are now trying to understand this translation in a work that we are doing to start abductive reasoning in this setting. But I think that what is interesting of this translation here is that it opened up a philosophical question that I will just put there without giving any answer, because I have no answer to this. And it was suggested by, when I was visiting Eduardo Barrio in Buenos Aires, I present him this translation, then he say, okay, but then what is the interpretation of Lukasiewicz logic? So if you can actually translate Lukasiewicz into probability logic, and everything goes so smoothly, it is true that Lukasiewicz logic is not a probability logic at all? Because I mean, there's a part of Lukasiewicz that is encoding probability, right? But this is already a sky high question. I mean, it's very abstract, doesn't have any possible even answer, right? But let's try to give an answer to it. Because the first one was a syntactic translation, so just a logical translation that preserves validity, okay? But there is another kind of translation that can be performed between the two languages, which is much more effective. And it uses another language, not the algebraic language, not the logical language, but the geometric language. And how it goes. But remember that the previous translation needed to translate the axiom of probability functions. Okay, probability was encoded by translating, for instance, additivity. The additivity formula, the additivity axiom is translated in Lukasiewicz setting. Now, geometry, well, basic geometry, I mean, finite dimensional, Euclidean geometry, allows for another kind of interpretation of probability. And this is due to a foundation of probability that is due to Bruno De Finetti, who studied the foundational aspect of what he called subjective probability theory. I will not go into the details because I could spend hours speaking about this, and you don't want me to speak hours about this. Now, if you want, we can spend days actually discussing about his theorem. But for the moment, what is important to know is that the interpretation that De Finetti was using to prove his theorem is fully geometrical. So what he does, what he did actually, is to interpret the probabilistic value of an event as a fair price, so as a number that represents how much you would pay to participate in a certain betting game. And everything was led by this notion of coherence. So no axiom whatsoever were introduced by De Finetti. He said the axioms are Kolmogorov probability theory. De Finetti is just based on a very intuitive notion of coherence that is defined on some specific betting games between players. And it's like a rationality principle. It's not axiomatic thing. What he proved is that under this condition of coherence, if your assignment, so you start just with a bunch of events that do not form a Boolean algebra, there is no algebra here, just a bunch of events, Of course, there is algebra hidden, but he used to say, no, there is no logic here. There is no algebra. Of course, there is, but he was hiding things. So if you have a bunch of events and just numbers assigned to these events, so it's an assignment beta on this set, the reals, he said, well, let's define the notion of coherence for these functions beta. And the theorem says that when beta is coherent, then actually, if and only if, there is a probability function that extends the assignment. So coherence means that the numbers you're assigning to the events are coherent with the Kolmogorov axioms of probability theory, right? So this is the mathematical version of it. Let's say analytical version of it. The geometrical version of it is that the set of all possible coherent assignment, and now we are encoding probabilities because every coherent assignment corresponds to at least one probability, the one that extends your assignment, has a very clear geometric interpretation because it is just a polytope in a finite dimensional space. Actually, something that we proved, I didn't put a slide on it, but what we proved with Sandro and Sarah is that every polytope can be seen as the polytope of a coherent set, which is quite strange, but actually it works. So probability now is not encoded in axioms, not encoded in the translation of the axiom in Lukasiewicz logic. It's encoded in just a polytope on some real space, right? Polytope is also a finite generator. So is a bunch of points, and then you take the convex combination of these points. And coherence. So before, remember that the theory, the definitive theorem says that an assignment is coherent if and only if there is a probability function that extends blah, blah, blah. Here, an assignment is coherent if and only if the point, because now we can see the assignment just as a point in this space, this point belongs to this set or not. So being coherent with probability functions or probability axioms is just a problem of belonging to a set or not. And this set is a clear representation because it's just a rational polytope. Rational means that the extremal points of this polytope are rational numbers. In this case, are even integer numbers because we are classical events. We have classical events. So just to have an idea, if you have your events, phi1, phi2, and phi3, that are represented by this binary encoding, what you do is you take the projection of this matrix, if you want, so the rows of this matrix, and you have this point, Q1, Q2, and Q3, right? You put them, these points in Q1, Q2, and Q3 in this case, in the cube. And you take the red triangle, which is the convex combination of them. This is the coherent set. So all what you have to know is what are these points? 3 points defines probabilities. So probability becomes, so being coherent, the probability becomes belonging to this set, belonging probability. And then we can extend the previous completeness theorem, right? So what Hayek, Esteva, Godot proved is that deduction in FP corresponds to semantic consequence with probability functions. And then you can add coherent maps very easily because every probability restricted to the set you want, just a coherent map by definition, and also the other way around, because if you can find a move that extends it, but it also becomes a geometric thing, because if there is a coherent map, then the point that this map represents in the geometric interpretation belongs to the set that you want to the coherent set associated. So logic, probabilistic model, partial models, because coherent just speaks about some events, not all the algebra, just a subset of events, and the geometric interpretation, right? Everything is equivalent up to this stage. And now it's interesting to make the comparison with Lukasiewicz logic again. Because for now we forgot about Lukasiewicz logic, but this is the same result if you forget about P. If you forget about the probabilistic modality, you have this result in Lukasiewicz logic. Because in Lukasiewicz logic, every evaluation can be regarded as a point in a certain cube. You have satisfiability is because you have a homomorphism of the free algebra to the reals that assign 1 to your formula, or you can just see this homomorphism as a map, a partial map on just the variables of your language, the reals, and then you extend it by truth functionality. So if you look at these two results, they are almost the same. But this is probability, this is Lukasiewicz. What changes? So again, let me summarize this with this table. Deduction, and you can translate one to the other. Homomorphisms becomes probability measures. Evaluation, logical evaluations are just coherent maps. And the relation between these two is very similar to the relation you have between these two, because essentially it is an extension theorem. The point in the cube is a point in the coherent set. And this is the basic thing. This is the important thing now. Because you can say, okay, Lukasiewicz logic evaluates formulas choosing a point in a cube, right? Probability logic is the same. So evaluate formula choosing a point, not in the cube, in a subset of a cube, in the coherent set. So if you have the formula x1 plus times x2, which is this shape here in Lukasiewicz, this is the representation of the formula in the free algebra. If you want, you want to know the value of this formula in this point v3, then take the value that this function takes on this point. This is the geometric, the way you can interpret Lukasiewicz formulas in geometric terms. Now, the thing is that if you have this formula here, every point is a good evaluation, because Lukasiewicz logic has no restriction in this sense. You can take every point to evaluate the formula. On this point, the formula will have value 0. Now, if you take the formula, the equivalent formula, the probability formula that arises from this, which is p phi 1, p phi 2, not every evaluation is correct, because you have to take care that now we have these two events, and not every point is a coherent assignment of these two events. Just to make an example, if your events are heads or tails in the coin tossing game, you cannot assign them 1/3, 1/3. But no probability will give 1/3, 1/3 to both, to them, right? It can be 1/2, 1/2, 1/0, 1/3, 2/3, but not 0/0, not 1/1. So you have to discard some of them. So if you just look at the one that are correct evaluations, then you do the same. In this point, the function takes this value, right? So it is, as in Lukasiewicz, restricting the domain of points to a certain very specific set. This is the message, right? And there's an extra step that we can do, because then, thanks to this geometric interpretation, we can move to the algebraic models of probability. And now we go to the, how much time do we have? Ooh, okay, can even slow down. It will be the hard part, sorry. So for the moment, we have seen that a probability formula can be evaluated as if it is a Lukasiewicz formula, but restricting the domain of the cube to some specific set that we can compute. I mean, the set is computable. It can be computed with algorithms, something that you know how to do it. But we can make an extra step. Why? Because polytopes, and in particular polyhedra, so rational polyhedra, are not nothing from the point of view of Lukasiewicz logic. They play a fundamental role in this theory. Actually, Lukasiewicz logic can be seen as the logic that reasons in terms of polyhedra. And this is the connection. This is due to a couple of papers, due to Vincenzo Marra and Luca Spada. They published this one in Studia Logica, the other one is the Annals of Pure and Applied Logic, in which they show that there is a certain class of, I mean, remember that the equivalent algebraic semantics of Lukasiewicz are MV algebras. Okay, the basic models are 0, 1, but you can even take the algebra of functions, like the one I showed you before. the MV algebra of all these functions, and you get the Lindenbaum algebra. So it's not any MV algebra. This is a very important one. Now, can you encode the restriction of this function to some domain? How to do that? Because remember here, we took a Macnaghton function, and then we just look at this yellow triangle. So we are restricting the function, not this one, we're restricting all the functions to this domain, and we get probabilistic evaluations. So what it means from the Lukasiewicz perspective to restrict functions to a certain domain? Well, it is just the algebraic operation of taking a quotient. Quotienting an algebra in Lukasiewicz logic is restricting function to a domain. And importantly, depending on the domain, on the topological, on the geometric aspects or definition of the domain you are considering, then you can capture certain relevant classes of MV algebras. For instance, if, now let me go to the slide because I have a picture. You have all MV algebras, free MV algebras, so algebras of Macnaghton functions, piecewise linear, whatever. Now, if you restrict on sets that are closed in the topology, you are essentially characterizing what are called semi-simple MV algebras. So MV algebras without infinitesimals, they're a very nice class of MV algebras. If your domains are not just closed, but they are polytopes, so they're finitely generated, polyhedra, rational polyhedra, so finite unions of polytopes, then you have a subclass, because this is a particular case of this. And the subclass is a class of algebra that are called finitely presented. Finitely presented MV algebras. Now, what we will do, we will restrict once more, instead of any rational polyhedra that can be not convex, we want to restrict to this specific coherent set that are polytopes. Not just polyhedra, but polytopes, which is a particular case of this, and then the algebra will be a subset. And we define this class of algebra that we call coherent MV algebras. So coherent MV algebra is just a quotient of a free algebra. So you take an algebra of functions, you restrict to the correct domain you want to deal with, and you define in this way the class of coherent MV algebras, right? Those are not a sub-variety, is not axiomatizable. It's not the equivalent algebraic semantics of the probability logic, because the probability logic is not algebrizable. Let me be precise on this. But there is a class of algebra that represents the probabilistic value that you assign to the formulas. And what can we prove? Well, we can prove that under a very specific interpretation of the formula in these algebras, we have completeness. So the probability logic, let me summarize this part in this way. Probability logic is not algebrizable. It doesn't have what is called the equivalent algebraic semantics, like Lukasiewicz has in the class of MV algebras, but it has what we used to call algebraic models. Not an algebraic semantics, are algebraic models, because if you choose the right interpretation of the formula in these algebras, then you have soundness and completeness. So deduction, probability standard models, coherent models, geometric models, and finally also algebraic models for probability. The logic that we are considering here is still the FP logic. So it's a probability logic with all the bad properties of a probability logic, but it has an algebraic interpretation. I wouldn't say, again, it is an algebraic semantics, because it is not, but it's a class of algebraic models for probabilistic reasoning. So probability logic, fuzzy logic is about algebras, true. Probability logic is about measures, but sometimes the measures becomes algebras, as in this case. So these algebras encodes the measures. I mean, it's a very long encoding. It's not just a straightforward encoding. It's made of several steps, but eventually we have these algebraic algebras for, the algebraic models for probability. And those are the steps. So in this also try to summarize, also to convince you the cooperative nature of these two theories, no? Because we started with this, our logic FP, I have this point, I don't know what I had to climb. So We have the logic with our language axioms. Okay. Now we have this translation. We have the translation that we showed before that allows to prove standard completeness. So you translate to Lukasiewicz in a certain way, you have standard completeness. And then this is if you want, the contribution of fuzzy logic, because okay, standard completeness is because Lukasiewicz logic is standard complete, and so it's a contribution of Lukasiewicz. But there is also a contribution from the probability theory. So the finite coherence theorem allows to move from this standard model to coherent models, and then from here to here in the geometric sense. I mean, this is almost the same thing, right? But this is the contribution of probability. And then we have the duality between this very special NV algebras and the geometric object that are represented here. And this is the Marra-Spada duality. So from logic FP, we get these algebraic models, the coherent algebras. And from here, what can we do? Because remember, being algebraizable is a very nice property for a logic, because then you can study for free. You have results for free. Interpolation, amalgamation, unification, algebraic unification, generalization as well. I mean, there are a lot of syntactic properties that are just for free if you study the class of algebras. Here, you cannot have these results for free, because again, you have algebraic models, but the logic is not algebraizable. Still, you can use algebraic models to understand if those notions can be studied algebraically for the logic. And we have two examples. The first one is about unification, the other one about functional representation. Functional representation is quite important because essentially, at least from my perspective, tells you, again, what fuzzy sets, in this case, what fuzzy sets are represented by your logic. So Lukasiewicz logic is a logic of McNaughton functions. So those are the fuzzy set that Lukasiewicz logic speaks about, right? And for any other logic, like product logic, Gödel logic, there are different representation of fuzzy sets. So it is a quite important thing to understand for the probability. But this is eventually, this is a fuzzy logic. FP stands for fuzzy probability logic. This is the name they chose, right? So very briefly, I don't want to give details on this, I want just to show you that now we can use these models to study or to get applications to syntactic reasoning. The first one is unification. What is the result we leverage to understand unification in the probability setting? Is a theorem by Ghilardi, Silvio Ghilardi, in 1997. He gave a representation of syntactic unification. Means you have, what is unification, right? So you have formulas, and you want to find a substitution that makes all them equal. It has an algebraic version, which is called algebraic unification with no fantasy. The name is what it is. I won't give you any detail, but the important thing is that everything goes around this notion of projectivity. So Ghilardi's proof uses a very special property of algebras, if you want, of Boolean algebras, if you're in classical unification, but also the structure that is that algebras have this property of projectivity, whatever it is. Now, what we realized with Sarah when we study the first semantics, the algebraic semantics, is that these coherent NV algebras are projective, whatever it means. And then we can try to generalize Ghilardi's result to this setting. Again, you have to do everything from scratch. There is nothing free now. We can follow the intuition, but we cannot use any result for free. And then we managed to prove, in fact, that there is a notion of probabilistic substitution for this language. The logic, for the logic, we can study the unification problem. Sorry, the unification problem in algebraic manner. And we proved, if you remember, for example, classical logic as unification type is unary. So it's the best possible case. Then you have, so the unification types can be unary, finitary, infinitary, and nullary. Nullary is the worst case possible, meaning that the unifiers of your formulas, usually they have a omega anti-chain. So I mean, you never get the most general unifier in this sense. There's no way to get it. And unfortunately, yes, we can study unification for this logic, but the result is quite bad. At least now we know the unification type is nullity. So it's the worst possible case for this logic. The other topic is functional representation. This is something that is really straightforward now that you know how to build the algebras, because algebras, coherent MV algebras are algebras of function restricted to the domain. So what would be a function, so a formula, how you represent the formula of this language in terms of functions? Well, you take the Macnaghton function corresponding to the outer Lukasiewicz formula, you restrict in the domain. This is the case, for instance, of coin-tossing game, head and tails. Head and tails are just two complementary events. So one is like Q and the other one is not Q, right? So Q not Q has this coherent set as polytop, just a line, just a segment. This one. A huge triangle is the truth function of the minimum, which is in fact the function that you are going to represent. But then we have to restrict just to this domain, and we get this strange triangle here. So this is the function, the probability, the function that represents the probability formula PQ meet P not Q. Okay, so not surprising, but at least now we know how to represent functions in the formulas in this. This is another case. This is again head and tails. And this is a Macnaghton function. You don't know how the Macnaghton function behaves in this part, but here it behaves in this way. It's piecewise linear. This is another example, for instance, right? So they are the function that arises by these formulas. Okay, done. So let me give you a last message that I think is could be interesting to highlight. The whole thing is not, I mean, we didn't search for algebraizability of probability logic, but we found this algebraic model that somehow resembles algebraic semantics for probability via this translation and further translations. What is relevant, maybe not for this community, but for the community of artificial intelligence, to which I try to speak sometimes, to convince them that this logic is quite a nice one. This logic, this is a result by Paolo Baldi, Peter Cintura, and Carlos Noguera. The logic that we saw today is the same logic that is mainly used in knowledge representation and reasoning, which is Halpern, Megiddo, and Fagin logic that they call AX-prop. It's the same. So there is a translation, the syntactic translation of the two languages, right? But this is so super ugly axiomatization. This logic is super nice because the axiomatization are four axioms and a deduction rule. If you look at this, if you look at the axiomatization of this, it's quite ugly. Still, that community is not accepting our. So this is a kind of problem. We are working on it. And eventually, we'll convince them that it makes sense. So we saw that this logic lacks many properties, truth functionality, structurality, so it's not algebraizable. However, we found these algebraic models that can be seen as some way to give an algebraic representation of the form. This is a message for the people from formal logic. It is not even a quasi-variety, so there's not an algebraizable logic associated to these algebras. Okay. And those are, I will not go into the details, but those are basic properties that you study in algebraizable logic, in abstract algebraic logic. Another question is, if we can study this in this setting for probability logic, of course, adapting the proofs, is nothing is free, but they would have really nice probabilistic interpretation. For instance, the joint embeddability property or the amalgamation property that corresponds to interpolation in algebraizable logic, here they could correspond to, this is just a claim, to what is called the fundamental theorem of probability. That means if you have a partial probability on some set of events, and then you add an extra event, how we should evaluate this event? Where? Okay, can you extend the coherent assignment to another event? This is Boole called it the fundamental theorem of probability. Well, many years ago, but still. This should correspond to amalgamation or Robinson consistency lemma. Now again, what is the relation between fuzzy logic and probability in light of these results? Oh, no, I'm confused, honestly. I still have to think about it, but knowing the differences allow also to understand better both theories. No. Finally, just final slide. We saw the logic FPL. So for probability on classical events, but more or less the same thing can be done if you want to use fuzzy events. Actually, the paper with Sarah in the Annals of Pure Applied Logic uses fuzzy events, so Lukasiewicz events, non-classical events, or different measures. Instead of probability, you can use belief functions, necessity measures, possibility measures, depends what you want. If you have a geometric interpretation of your uncertainty theory, then you can try to do this. And I'm pretty sure it works. So you can do it for belief functions, imprecise probability, more or less, possibility and necessity, yes. Ranking function is something that we are trying to understand with Luis and Giuliano Rosella. Well, this is a list of possible extension of this approach to many other uncertainty theories. So to connect not just probability with fuzzy logic, but uncertainty in general with fuzziness or vagueness in this. And, well, basic bibliography. Thank you very much for your attention.
It was a really very interesting talk. We have a couple of minutes for discussion. So please. As usual, Irina.
Yes.
Yeah, thank you very much. It's difficult, of course, to ask something, yeah, because I have a lot, and to formulate the special one. Okay, I will try. Look, first of all, coming back to the foundations, yeah, why we are working in this direction? Because we want to apply machinery of logic, yeah, in order to prove some facts, yeah,
Yes.
from another theory, or vice versa. Yeah, we have some facts, yeah, from, say, probability and related logical machinery, yeah, and using this, for example, there is something very interesting in probability which we cannot have in logic, and therefore we would like, yeah, to also to bring, yeah, this new information about events, actually everything about this, yeah, to logic, yeah, right. So
Yes.
this is the main purpose, yeah, and the main, yeah, and again, just tell me if I'm correct, yeah. The most tricky, yeah, is that probability is based on the sigma algebra, which is a certain structure of subsets, yeah. And on the other side, yeah, we have Lukasiewicz, and the model is just some, say, subsets, yeah, of reals or whatever, yeah. So in this case, yeah. And actually, the nature, yeah, of both, yeah, is different, and therefore the main trick is how subsets can be interpreted as points in a certain sense, yeah, or vice versa. So this is the most,
Yes,
yeah.
but up to a certain extent. So, for instance, what you say is true, but let's put it clear. Probability can be many different things, and we choose a precise way of understanding probability that allows this interpretation. For instance, probability can be seen as the integral of functions given a sigma additive measure, right? This interpretation of probability doesn't work in this case, but as far as I know, because what you have to encode is not a finite bunch of information. What the finitives theorem allows is to encode the same information, but we are still speaking about probability, but in a way that is finitary. And since it is finitary, that translation works. Yes. No, the fund has to choose which is the right level for the translation.
Yeah, actually, I do integral, but and this is the most how we treat, say, subsets using some aggregated information about.
Yeah.
Okay, so sorry, but no long discussions because there are some other people. For example, uh-huh. Okay, so somebody else who would like to ask or comment? I didn't want to.
It's the answer to the question. With the relation between the two theories, it would be really, if you want to think about it.
Okay, if there is nobody, so thank you very much. We learned a lot from you. And thank you.